So as we've seen, we now know that we can calculate our binomial coefficients and we don't actually have to draw up Pascal's triangle each time. We know it's the same as our combinations, so n factorial, k factorial, n minus k factorial. Well, just for a bit of fun, let's prove that NCK is indeed n factorial on k factorial, n minus k factorial. So I'm going to prove it's true for k equals 0. Well, 0 would be the first case, because NC0 is the first coefficient. So the left-hand side would be NC0, which we know is 1. We defined that to be 1. The right-hand side would be n factorial on 0 factorial, n factorial, which also turns out to be 1. So yes, left-hand side equals right-hand side. It is true for k equals 0. I'm now going to assume the result is true for k equals r, where r is some integer. In other words, I'm going to assume that NCR is in fact n factorial on r factorial, n minus r factorial. We now want to prove it's true for k equals r plus 1. So we're going to prove that NCR plus 1 is n factorial on r plus 1 factorial, n minus r minus 1 factorial. Now, we know that n plus 1 CR plus 1 is NCR plus NCR plus 1. That was our rule for creating Pascal's triangle. Well, if I rearrange that, I get NCR plus 1 is n plus 1 CR plus 1 minus NCR. But I have assumed that NCR is n factorial on r factorial, n minus r factorial. So therefore, I can assume that NCR, there it is, the second one, and the first one must be n plus 1 factorial on r plus 1 factorial, n minus r factorial. Okay. Now we'll just play around with our algebraic fraction here. Common denominator is r plus 1 factorial, n minus r factorial. Top has a common factor of n factorial. The n minus r will now cancel with the n minus r factorial. And voila! We have n factorial on r plus 1 factorial, n minus r minus 1 factorial. Hence, the result is true for r plus 1 if it's true for r, but hence the result must be true for all positive integral values of n by induction, because of course we've shown it. Let's move on to the next bit. So the whole point of this topic, what is the actual binomial theorem? Well, that's it in all its glory. 1 plus x to the power of n is nc0 plus nc1x plus nc2x squared, and so on and so on and so on. The general terms in the middle there, nck x to the k, which I can write in some notation and save myself a bit of time. We just write the general term in there, so nck x to the k, and we're saying we're going from k equals 0 to n. So sometimes you'll see the some notation used just basically to say writing all those terms out. And nck is our, well, n factorial on k factorial, n minus k factorial. Now, there's always going to be n plus 1 terms. Remember, we start at NC0 and go up to n, so you always have n plus 1 terms. Now, that's the binomial theorem when it's 1 plus x, very limited in what you can use it for. So, of course, we could extend that out to be a plus b to the power of n. The general term now would become nck. B is to the power of k. I always think of that one first, because then I say to myself, oh, well, the other power must be n minus k, and I just do a subtraction and work out the other power. Alright, so evaluate 11C4. Yes, we've lost our calculators. We actually have to work it out. I know, but it's fun, because you get 11 factorial on 4 factorial, 7 factorial, which if I roll out the factorial, but cancel off the 7 factorial, then the top becomes 11 times 10 times 9 times 8. I've cancelled the 7 factorial. And then on the bottom we get 4 times 3 times 2 times 1. And then we just have fun cancelling, because I can look at this and go, oh, what do you know? 4 2s are 8. That cancels. And 3, well, that goes into 9 3 times. So I've got 11 times 10 times 3, 330. Who needed a calculator? We can just Okay. So we're going to find the value of n such that NC5 is NC8. Now, yes, I could go back to factorial notation and solve that. But if we use the symmetry of Pascal's triangle, then we know, remember, that NCK is always the same as NCN minus K. In other words, n in this one must be 13 because 8 and 5 are 13. So one like this, NC7 plus NC8 is 20C8. Again, yep, I can change it all to factorials unless I recognise it to be, hang on, this is the one where we say to create a term, we go to the term above. So if that's the case, then n in this one must be 19, the row above. So knowing those relationships can save some time. Find the fifth term. Now, we don't expand the whole thing out. The first thing we do is write out the general term. Now, some people say the general term is term k. Personally, I say it's term k plus 1, because to me it makes more sense to start with the first term rather than start with the noughth term. So that's the only reason I call it k plus 1. But the general term will be 11ck for this one. I always go to the second term first, so minus 3 on b to the power of k, which means the other one, 5a, must be to the 11 minus k. They want the fifth term, so that's when k is 4. And we get 11c4, 5a to the power of 7, minus 3 on b to the power of 4. Well, there it is in unsimplified form. In a lot of these cases, it's quite okay to leave it unsimplified, because if you did have to work it out, well, 11c4, 330, then 5 to the power of 7, 78,125. Negative 3 to the power of 4, 81. Oh, there's the answer. A really big number, I'm not even going to attempt to try and say. More commonly we get asked things like this. They're more interested to know the independent term, so the term that doesn't have an x value. So again, I'll work out my general term, but in this case I'll simplify the x's, because we want to know when is x to the power of 0. So all I'm really interested in is the x's. So the x squared to the power of 9 minus k. The x to the negative 1 would be to the power of k. I want that to be x to the power of 0. So tidying up with our index laws, we get k is equal to 6 for this one. So we want to find then that actual term. Let's sub it back into the general term. And there it is, in its unsimplified form.